My name is Samir Khan and I'm part of the product management team here at MapleSoft. My role here is to speak to our customers and help them better understand our tools, technologies and services. I'm very excited today to talk about our new version of Maple 2019. It was released a couple of weeks ago and it's a release packed full of features that provide value for all parts of our customer base. Now I'm going to do the bulk of this presentation within Maple. This is a broad overview of all of the areas and parts of Maple that we've improved. There's something here for everyone. If you're a professional engineer doing data analysis, or you're a mathematician solving PDs symbolically, there's lots of value in Maple 2019 for you. Now there's always more in every new release than I go into in a presentation like this, so I always have to pick and choose what I present. What I'm going to present is largely what interests me. Everything is described in detail on our website. So I'm going to start off with the advances we've made in advanced mathematics. Now, what keeps people coming back to Maple year after year? What keeps people updating and maintaining their license of Maple? It's simply the advances that we continuously make in pushing the forefront of computational mathematics backwards. We've made many advancements, many improvements to many parts of our mathematical engine, and these are just a few examples, and I've chosen to compare some results in Maple 2019 to the corresponding results in our previous version, Maple 2018. We've made many enhancements to differential equations, integrations, multivariate limits. We've improved the solve command. Simplification is much more elegant. And I think we can safely say that we're the world's leading tool for solving partial differential equations symbolically. We're far better than our closest competitor. This might just take a few seconds to compute, but here you go. Now there are many other advancements to Maple's basic math functionality. For example, we've introduced enhancements to graph theory, group theory, and many other parts of our math library as well. But let's put that to one side for the moment. Now, every release we try to make Maple faster. Sometimes we make improvements to the underlying infrastructure of Maple, and that benefits the entire functionality of the system. So for example, I think in Maple 17 or Maple 2015 we improved the garbage collection within Maple, which helps you to make better use of the memory on your computer. For this release we've improved a number of core functions, and I'm just going to concentrate on one, the factor command. This is a very common command that many people use. So here I've just started off by generating two random polynomials, and I'll just multiply them together and expand the product. Now, factorization has been enhanced for this type of problem within Maple 2019. So this took about 5 seconds on this laptop in Maple 2018 on the same machine. Now it just takes a small fraction of a second, less than half a second. That's a real tangible improvement that we've made to the performance of this very commonly used command. And we've made similar improvements to other commands within Maple as well, and those are described in detail on our website. We've made many significant improvements to our tools for statistics and data analysis, and I'm going to highlight a couple of new commands here. So least trim squares regression is a way of fitting a model to data in the presence of outliers. For this example, I'm going to start off by artificially generating a noisy data set that's equal to about 5x plus 50, but I'm going to pollute this with a few extreme outliers, as you can see here. Here I'm plotting the artificially generated data set. Let's say I wanted to recover this equation by fitting a straight line to this data set. Well, typically I'd use something like least squares regression, and there's the least squares command in the curve fitting package which does this. So if I apply this function, least squares, to this data, this is the equation I return. As you can see, the results don't reflect the equation that I used to generate the data because of the presence of outliers. However, if I use the new least trimmed squares command in the statistics package, the resulting equation more accurately reflects the underlying model, the underlying system. We also have a new command called the correlogram. This computes the autocorrelation of a data set and displays the result as a column plot. For this example, I'm going to import some sunspot data from the years 1700 and I think there's about 200 or 300 years worth of data. So if I apply this function to this data set, I get the autocorrelation of this data set displayed as a column plot with lines indicating confidence bands given a normal distribution. We've also made a number of significant enhancements to Maple's visualization tools as well. Now, this is one feature that I'll be using on a regular basis, SVG Exports. So let's say I've generated a plot like this and I want to export it to an external file that I can use in a presentation. If I use normal format like bitmap or PNG, if I resize the plot, perhaps expand it or contract it in a PowerPoint file, the result often becomes illegible, difficult to read, or pixelated. However, now I can actually export a file in SVG format. If I right click on the plot and I select export, I have this new option here. Just to show you an example, I'm just going to export this to a file called chart and save it. Now if I load up the file, this is the exported SVG plot. If I expand it, if I shrink it, if I zoom in or out, the plot maintains its crispness. It doesn't get pixelated or rasterized. I also have access to a number of new plotting primitives, which allow me to programmatically construct my own visualizations as well. They're used in this command, polygon by name, and they're also flexible and customizable. So I have shapes like circles, semicircles, rectangles, stadiums, half stadiums, super ellipses, super circles, and other more specialized shapes as well. Now, we've made significant enhancements to our tools for signal processing, and we've made a number of improvements to our tools for image processing as well. So let's go through these. I think this is perhaps the most interesting new feature in our tools for signal processing. You can now investigate the frequency spectra of irregularly sampled data. Let's look at this application. So here we're going to predict the orbital period of an exoplanet by analysing the radial velocity of the star it orbits. Now typically with astronomical observations and with many other kinds of observations as well, the data is not regularly sampled because of scheduling issues, cloud cover and so on. That means you can't use standard Fourier techniques to generate frequency spectra. Other specialized techniques need to be employed as well, and a common approach is the Lomsgardel approach. So here in the first column of the data I've imported, I have the Julian date. In the second column I have the radial velocity of the star the exoplanet orbits. Now if I were to plot the radial velocity against the date, this is what I would see. As you can see, the data is irregularly sampled. Now, however, I can apply a new tool for generating Lomsgardel periodograms to generate a periodogram of this irregularly sampled data. Here we see a peak at this point. This indicates that the orbital velocity of that exoplanet is around 60 days. Now there are many other applications for Lomsgardel periodograms. Anywhere you have irregularly sampled data, you can apply the Lomsgardel approach to generate the frequency spectra of that data. Here's another really useful function. We have a new function which extracts all the local peaks of a data set. It's a core new tool in the signal processing package. So we're going to start this off by importing a wave file and plotting its periodogram. And here we are. The first peak here is the fundamental frequency of the violin note, and everything else is a harmonic. So let's say that we wanted to find the precise location of all of these points. Well, in other versions of Maple you'd have to use the point probe tool manually and place it over each of these peaks to extract the peak point, but that's a very clunky way of doing things. But now, however, we have a new function in the signal processing package, find peak points, which allows you to extract all the local peaks and valleys of a data set, and there are intelligent options in find peak points to actually rule out spurious peaks or valleys, specify the minimum height of what you consider a peak, and so on. So here are all the peak points, so the point on the x-axis against the point on the y-axis, and if I were to overlay the peak points over the periodogram, this is what I would see. As you can see, I've successfully located all of these local peaks, and if I wanted to, I could modify the command to pick off the local peaks here as well. We've improved the spectrogram function, so now that you can specify the overlap in successive slices of the signal. Previously the overlap was hard-coded to 50%. So this would be the default behavior in older versions of Maple. However, now you can programmatically change the overlap as well. So I can generate a new spectrogram with an overlap of 90%. That means when I generate a spectrogram, each successive slice in time shares 90% of the same data as the previous slice in time. This actually gives you more resolution in the frequency axes at the expense of smearing out some of the detail across the time axes. It just gives you some extra control over the individual features that you want to pick out in the spectrogram. We also have new tools for calculating the real and complex spectrum and substrum of a signal as well. Now, this functionality is typically used in audio and speech analysis. Fundamentally, it allows you to simplify how you can extract information from the frequency spectrum from a sound signal. So if you were to plot a parallelogram of a sound, you'd have the fundamental frequency, and there may be some multiple harmonics associated with that as well. If you have multiple fundamental frequencies and multiple harmonics, quite often differentiating between the two is difficult. These new tools actually help simplify that analysis. They collapse the fundamental frequency and the harmonics of a sound into a peak, and some other smaller peaks as well. And this is typically used in audio analysis. And here's an example. So first of all, we import an audio file. Now, although you can't hear it, the audio file is actually polluted with an echo. You can use this new function, the real substrum, to identify the start of the echo. So we apply this function to the audio file, plot the result, and this is what we get. We get a few peaks here. Now, this large peak here indicates the location of the start of the echo. We can use this information to generate a filter that we apply to our data set to remove the echo. We can then take the data back to the time domain and plot the audio with the echo against the audio with the echo removed. So let's talk about this new function, FFT Shift. FFT Shift moves data in a matrix into a different position. Now, there are various options in the new command to specify how you want the data in the matrix shifted, but essentially the FFT Shift function is typically applied to move the lowest frequencies in the frequency transform of an image to the center and the highest frequencies to the corner. That actually results in a more meaningful visualization of the power spectrum. So for this example, we're going to start off by importing an image and placing it into our worksheet. Now, if we just take the Fourier transform of this image and visualize the spectra, this is what we get. The lowest frequencies are at the four corners, while the highest frequencies are in the center. Typically, to do any analysis or manipulation of the frequency in the frequency space, we need to shift the lowest frequencies to the center and the highest frequencies to the outside. And we can do that very easily with the new FFT Shift function. And if we applied that function to the FFT of the image, this is what we get. This is the periodogram of the image. Now, this just makes it easier to do frequency domain manipulation of this image. Let's say that I wanted to blur the image by applying a Gaussian mask. Well, what I can do now is very easily apply a Gaussian mask to the Fourier transform data, and then applying the inverse FFT Shift function, which simply reverses what FFT Shift does. I can take the image from the frequency domain back to the spatial domain, and as you can see, I've removed the higher frequency data, so I'm only left with a blurry image. None of the sharp edges that would be represented by the higher frequency data. Now, let's put the other new features in the signal processing package to one side. And let's talk about the improvements that we've made to the user interface. Now, we've streamlined the interface by moving some options to more logical places in the file system. This just makes it easier to locate the options that you want. We've also made improvements to the way data is displayed in the interface as well. Now, when you generate a matrix, you see the header of the data. So here I'm generating a large matrix, populating it with random numbers, and I see the header of the data, the top left hand corner. In prior versions of Maple, you'd see some information about the way the data is structured, the type of data, but frankly for most use cases that wasn't of much utility. This is far more useful. If I want to see the information that I would previously get, I can simply use the describe command. Additionally, when you import audio files, instead of seeing information like this, you actually get details which are actually of some utility in your analysis, such as the sample rate, the bit depth, the number of channels in the audio file, and of course the duration in seconds of the audio file as well. Now, one frequently used aspect of Maple is the unit system. I know many engineers who use units in Maple as a core part of their analysis. Now we've made it easier to insert units by reinventing our units palette. Previously, you had two units palettes, one for SI units, another for FPS units, and they gave you a limited number of units that you could insert. Now, with the new units by dimension palette, you can pick the dimensionality you want, such as frequency or force, and you get units, relevant units here underneath. This just makes it easier for you to find and insert the units that are relevant to your work. We've also made many improvements to our programming language as well, but I'm only going to show you one feature, one of the improvements that I really find useful. We now have C-style increment, decrement and assignment operators. So let's just say I wanted to add 1 to a variable, or I wanted to increase the value of a variable by 1. So previously I'd have to do something like this. However, now I can write something like this, a C-style increment operator. Now, where the real value of this is when this thing here, n, is computationally intensive to compute. Something like this is more efficient than this. So finally, I'd like to just highlight one of our new math apps within Maple. Each release we always add new math apps. These are interactive applications which let you explore a scientific or technical concept. We've added a number of new engaging math apps for this release, but this is probably my favourite, Day and Night Terminator. This allows you to examine the progression of night and day across a world map. So what's interesting is that I can move these sliders to say change the hour, and you can see how night and day progresses. I can also change the projection of the world map. And I can also change the color scheme used as well. Now that was all I wanted to demonstrate today. There is a lot more that we've packed into Maple 2019. We've added functionality, or we've improved the functionality of many other parts of our system. What I do encourage you to do is visit our What's New website. It's here. This describes everything in detail